begins, as most catastrophes do, with silence. No sirens, no emergency broadcast cutting into your favorite show. Just a soft flicker of light in the night sky, auroras dancing over places that have never seen them before. Miami, Houston, Singapore. People will step outside with their phones, filming the strange green and violet ribbons overhead, thinking they're witnessing something beautiful. They will be right, and they will be completely wrong about what comes next. Because 93 million miles away, the sun has just exhaled. Let's go back to September 1st, 1859. A British astronomer named Richard Carrington was doing what he did every clear morning, sketching sunspots through a telescope in his private observatory. What he saw that day had never been recorded before. A blinding white flash erupted from a sunspot cluster, so intense it lasted only 5 minutes, yet it was bright enough to be seen with the naked eye. Carrington had just witnessed the largest solar flare in recorded history. 18 hours later, the storm hit Earth. Telegraph systems across Europe and North America failed catastrophically. Operators reported electric shocks from their equipment. Telegraph paper spontaneously caught fire. In some stations, operators discovered they could disconnect their batteries entirely and still send messages. The storm itself was powering the wires. The aurora borealis was so intense that people in Cuba, Hawaii, and Colombia saw the night sky glow crimson and gold, close enough to the equator that gold miners in the Rocky Mountains woke up and started making breakfast, convinced it was dawn. It was, by every measure, one of the most extraordinary natural events ever documented. And here is the part that should keep you up at night. In 1859, humanity had almost nothing electric to lose. A few thousand miles of telegraph wire. That was it. No power grids, no satellites, no internet, no smartphones in every pocket. The Carrington Event was a spectacular light show with minor consequences because there was barely any electrical infrastructure for it to destroy. Now ask yourself, what happens when a storm of that same magnitude strikes a planet completely wired for electricity? We almost found out. On July 23, 2012, a solar storm of comparable, possibly even greater intensity than the Carrington Event tore through space directly across Earth's orbital path. NASA scientists later calculated that had this storm erupted just 9 days earlier, it would have hit Earth directly, rather than missing us by roughly a week's difference in the planet's orbit. Physicist Daniel Baker of the University of Colorado, who studied the event extensively, stated plainly that had this storm hit Earth, we would still be dealing with the damage today, years later. Another researcher estimated the economic cost at over $2 trillion in the United States alone, with recovery potentially taking 4 to 10 years. We dodged it by 9 days. 9 days out of billions of years of solar activity. That is how close we came, and almost nobody noticed. Now here's where things get uncomfortable, because this isn't ancient history, it's current events. Scientists track the sun's activity in 11-year cycles, and we are currently living through solar cycle 25. Solar physicists predicted this cycle would peak sometime around 2024 to 2025, and the data has shown it arriving stronger and faster than many models anticipated. Solar maximum isn't a single dramatic day. It's a prolonged, turbulent window where the sun's magnetic field becomes chaotic, sunspot activity spikes, and the odds of a major flare climb dramatically. That window doesn't simply switch off. The elevated risk period extends for months, even years after the official peak, meaning 2026 sits squarely inside the danger zone, not safely behind it. So let's talk about what modern civilization actually looks like from the perspective of a geomagnetic storm. We live inside an invisible nervous system. Power grids stretch across continents, their transformers connected by hundreds of thousands of miles of cable that act, quite literally, like enormous antennae. A severe geomagnetic storm induces what scientists call geomagnetically induced currents, surges of unexpected electricity that flow backward through these lines and into the transformers that keep our lights on. These transformers are not small, cheap parts you swap out at a hardware store. Large power transformers are custom-built, weigh hundreds of tons, cost millions of dollars each, and in many cases take 12 to 24 months to manufacture and ship. There is no national stockpile large enough to replace a mass simultaneous failure. In 1989, a geomagnetic storm, far weaker than Carrington level, knocked out the entire Hydro-Quebec power grid in Canada in just 90 seconds, plunging 6 million people into darkness in the middle of winter. That storm also damaged a transformer at a nuclear plant in New Jersey. That was a moderate event. A true Carrington-class storm striking today's grid could be an order of magnitude more destructive. Now, scale that up to the world we actually live in today, a world Carrington's Victorian telegraph operators couldn't have imagined in their wildest dreams. GPS satellites guiding everything from commercial airliners to the phone in your pocket to the precision agriculture that feeds nations are directly exposed to solar radiation with essentially no atmospheric shielding. Increased ionospheric disturbance during a severe storm can degrade or completely scramble satellite positioning data for hours or days. Airlines have already had to reroute polar flights during smaller solar storms because radio communications degrade near the poles. A truly severe event could ground global aviation on safety grounds alone. Then there's the satellite fleet itself. Over 10,000 operational satellites now orbit Earth, a number that has exploded in just the last 5 years thanks to companies launching mega constellations for global internet coverage. These satellites are vulnerable in 2 ways. First, direct radiation damage to their delicate electronics. Second, and this is something few people talk about, a severe geomagnetic storm heats and expands Earth's upper atmosphere. In February 2022, a relatively minor solar storm caused atmospheric drag to increase so much that SpaceX lost 38 brand new Starlink satellites within days of launch, as they were literally pulled back down into the atmosphere and burned up. That was a minor storm. Multiply that effect by the intensity of a true Carrington-level event, and constellations providing global internet, banking synchronization, and emergency communications could be crippled or destroyed in a matter of hours. And banking. Modern financial systems run on precisely synchronized timestamps, largely dependent on GPS signals to record transactions down to the millisecond. disrupt that timing infrastructure and stock exchanges, international wire transfers, and even the systems that verify your card payment at a grocery store checkout could stall or fail. In a fully networked global economy, a communications blackout lasting even days, not months, could ripple into supply chain failures, halted shipping, and stalled just-in-time inventory systems that most cities depend on for food and medicine within 72 hours. This is the part of the story people rarely connect to solar physics. Our just-in-time global supply chains were never designed with a multi-day communications and power blackout in mind. Grocery stores typically hold a few days of inventory. Fuel distribution depends on electronic payment systems and pipeline control systems that are themselves vulnerable to induced currents. Water treatment plants require continuous power for pumps and purification. None of these systems were engineered around Victorian-era telegraph resilience. They were engineered around the assumption that the grid simply doesn't fail everywhere at once. So why does 2026 specifically keep coming up in scientific and preparedness conversations? It isn't because any scientist has predicted an exact date for a storm. Nobody can do that. Solar flares remain fundamentally unpredictable in their precise timing, even with our best current instruments. What scientists can say with real confidence is that we are inside the most volatile stretch of the current solar cycle, a stretch when the largest flares in the historical record, including events comparable to Carrington, have statistically clustered. The sun's activity doesn't fall off a cliff the moment a cycle's official peak passes. It tends to producing some of its most intense individual flares in the 2 to 3 years following maximum, as the magnetic field reorganizes itself in increasingly unstable ways before settling down. Agencies have taken notice. The NOOA's Space Weather Prediction Center now issues real-time alerts the way meteorologists track hurricanes. The UK officially lists a severe space weather event on its National Risk Register, treating it with the same institutional seriousness as pandemics and major flooding. Multiple governments have run classified tabletop simulations modeling a Carrington-class strike on modern infrastructure, and reporting from those exercises has consistently described the same conclusion: cascading multi-week to multi-month regional blackouts, satellite disruption, and economic damage measured in the trillions of dollars.
None of this means civilization ends. Let's be clear about that. Human beings are not fragile, and modern infrastructure, while vulnerable, is not defenseless. Utility companies have installed some geomagnetic monitoring and protective relays since the 1989 Quebec blackout. Satellite operators can, with enough warning, place spacecraft into safe modes that reduce damage. NOAA's warning systems, imperfect as they are, can give anywhere from minutes to about 30 hours of advance notice depending on the type of solar event. Enough time, in some cases, to take defensive action. But here's the uncomfortable truth underneath the science. Modern civilization has built extraordinary complexity on top of a fragile electromagnetic foundation, and most people alive today have simply never lived through a moment when that foundation failed. We've built a world where losing the internet for an afternoon feels like a minor inconvenience, not a symptom of just how dependent every single system, food, water, medicine, finance, communication, has become on a layer of technology that a single, ordinary, natural event from our own star could disrupt in hours. Carrington storm in 1859 was not an anomaly. It was not a freak accident of nature. It was the sun behaving exactly as it always has, exactly as it always will, because that is simply what stars do. We are the anomaly. We are the species that built a hyper-connected, satellite-dependent, electricity-hungry global civilization directly underneath a star that periodically, unpredictably, and without any obligation to our convenience releases the kind of energy that dwarfs anything human beings have ever engineered. So when the auroras appear over Miami, over Houston, over cities that have never seen the northern lights, when people rush outside with their phones to record the beauty of it, remember that beauty and catastrophe in the story of our sun have always arrived together. The light in the sky isn't a warning shot. It's the visible edge of an invisible storm already reaching Earth's magnetic field, already inducing currents in wires we can't see, already testing every system we've quietly, collectively decided to trust without ever asking what happens if it fails. We don't know if 2026 will be the year. Nobody does. Not NASA, not NOAA, not a single solar physicist on Earth can name the date. But we do know this: the sun has done this before. It will do it again. And the only real question left is whether we'll be ready or whether we'll be standing outside, filming the sky, completely unaware that the countdown has already started.